Okay. Hello, everybody. It is my great pleasure to open up this new series of talks in the new semester, together with our well-established and famous speaker, Vysoký. And I'm sure this time is somehow prominent because of the date, the 29th of February.
Wow.
Yeah, this is what I'm pretty convinced shouldn't come anytime sooner in the future. So I'm sure Jan will grab this opportunity without effort. So Jan, together with his topic, flows on graded manifold, is coming for this time, and we are pretty happy that you came for us to say something.
Okay, so thank you very much for an introduction. So there is one important announcement that this is not a finished work. So there's plenty of blank spaces here and there. So it's just first ideas. We basically now already have an idea how it will work. You know that in ordinary differential geometry, the flows are kind of one parametric families of diffeomorphisms or local diffeomorphisms, which are associated to each and every vector field on the manifold. And since on graded manifolds, there is easy way how to define vector fields, but one also expects to obtain something like flows. So that's the idea. We have flows in ordinary geometry. We want to have flows in graded geometry. And why are flows important? Because, of course, for example, for dynamical systems given by some vector field, this is what you are seeking. If you are given some vector field, you want to integrate it to actual motion. For example, Hamiltonian equations can be rephrased in this way, seeking flows of Hamiltonian vector fields. So this will give you a family of all motions starting from all possible starting points, from all possible initial conditions in your phase space. So you definitely want to have this like it is. And you also want it because flows are used in many theorems and many considerations in geometry. You can integrate a vector field to a flow and do something with it. For example, Frobenius theorem is basically based on the flows of vector fields. So I will start by first examining a bit ordinary flows. So this is maybe too small, but
it's fine.
It's fine. Okay. So first of all, in my consideration, I will have a general manifold, but to keep things simple, I assume that it's compact. So for the whole seminar, I can avoid discussing the fact that flows cannot be sometimes defined globally. So if M is compact, flows can be always defined globally. But I promise you that everything I am telling here works also for general M. So it's just a technical simplification for me to save some time. Right? And so if you have a vector field on your manifold, so you have a vector field and flow, maximal flow sometimes, if you want the biggest domain you get of X. It's a smooth map, theta, which goes from M times R to R. And you want some conditions imposed on your theta. So first of those is that if you differentiate at every point t and every point n with respect to t, so this, if you fix n, you get some curve in your manifold n, and you want this curve to be
goes to n, right?
yeah, sure. That's important consideration. It's a given group, so it's not really.
No,
Yeah, like here. Ah, here, yeah. Okay. You're nitpicky. Wrong letters, wrong order of values. Okay, so if you differentiate it, so if you fix this point n, you want to get integral curve to a vector field, so you should really get vector field x evaluated at point theta and t. So this kind of one of theta to satisfy this differential equation, and then of course your integral curve at time 0 should start from n, so you get these, differential equations together with some initial conditions. So that's first thing you want. The second thing you want is some group-like behavior. There are various names for this property. Sometimes it's called one parametric subgroup of diffeomorphisms, blah blah blah. But it means precisely this condition. So if you first flow by time s and then by time t, you want to get precisely flowed by time t plus s. There is a kind of more convenient notion for this, so you can simply keep this first input empty and define this thing. And this thing is a map from m to n, and these maps really can satisfy this. Okay, and it is a well-known fact that every vector field has such a flow. So it's theorem in classical differential geometry textbooks. Kind of every x has a maximum flow. Now, because in gradient geometry, there is always a problem with points. So you really don't want to write functions as something evaluated at some point. You want to rephrase everything as some diagram of maps. So you want to do everything more category friendly way, I would say. So how does one formulate this problem in diagrams? So one simply observes that if you take R with plus, this is just an abelian Lie group, right? Where plus is multiplication. It's multiplication. And a map which goes kind of, if you want to define unit of a group in some category, you formulate it as a map going from a terminal object of your category to your group R, and it's unique, and it's just a map which assigns to this one point set 0 in your group, which is a unit of your group. And then there is also unique map which goes from M to R, which also assigns to every point 0. Right? So basically, how this in more general category you would construct this as a terminal arrow going to * and then 0 to R. So you can always get all kinds of zeros going from any object in your category to your group, particularly this one. And then you can formulate this as a two commutative diagrams. So then the diagrams, which I will now write down. So first of them is so theta goes from n times r to n. Here we have identity, and here we have basically the zero section, which I can write as map 1m 0m. And this diagram commutes if this property is satisfied, right? And then there is another bigger diagram, which looks like this. So if you want to be precise, you have to distinguish these two guys, but there is some isomorphism going between the associator and your m. Here we get map theta times identity on R. Here you have what? Here we have identity on M times this multiplication map plus going as map from R times R to R. And then you have theta here. And this is precisely this property, if you think about it. Right? So this is precisely this property here. And these diagrams commute. And how you can say it in terms of free groups? This really just means that theta is a right action of this Lie group R on N. Right? And this is precisely doable in any category. So in any category where you have groups, group-like objects, this is a categorical notion of an action. Okay, so this is this kind of combination of this requirement and this requirement. But what about this one? How to formulate this one? And you can think about it as follows. So your R is a Lie group, and coordinate vector field corresponding to your single real variable is just a left invariant vector field. It's left invariant vector field corresponding to its value, basically to its value at 0, which is an element of Lie algebra. This is Lie algebra. Yeah. Lie algebra of R is R. So this is really just an element of the tangent space at the unit, which is Lie algebra. So this is really just a vector field, which is left invariant and also right invariant because they are C-grid. And I claim that this differential equation here just means this differential equation just simply says that X is an infinitesimal generator with respect to this action theta corresponding to this is the algebra element. Yeah. And that's it. That's how you can reformulate this in kind of Lie group language. So basically, if you look for a flow, you look for a Lie group action of R on your manifold such that your given vector field is its infinitesimal generator, fundamental vector field. And this can be, okay, so you can ask, can I write this in my category of graded manifolds, which I will explain later how it looks like. So how can I formulate this in more, again, because this is usually defined again using points, like you infinitesimal generator at point n is you calculate the exponential of your Lie group element and then map it to using your action and differentiate it, and you collect those all those tangent vectors and you get a vector field. But there is a nice way how to reformulate this kind of in terms of functions. So what you can do, you can construct vector field which is denoted suggestively as 1 tensor delta phi, and this is a vector field on the product of M and R, and it's just obvious lift of this vector field from the base. So simply it's just a vector field on the Cartesian product which differentiates with respect to this global variable on M times R. So you can always find this lift, it's uniquely determined, and then you can rephrase this property. So let me know this star property star, and this property star is then equivalent to the following equation. So you can state, okay, so you can first state it like that vector field, this vector field upstairs is theta related to x. So that's one way how to reformulate this. And this is how you define infinitesimal generators in graded geometry for any graded Lie group and any graded manifold eventually. And you can write this simply as a and why this is useful, because you can write this as in terms of pullbacks. So this can be rewritten as this is a vector field, so it's an operator of functions on functions, right? On smooth functions, and then this theta relation really means that this theta intertwines, theta star pullback with theta intertwines the action of two vector fields. So this really can be written simply as this equation. So we first pull back your function from, and this has to hold for all functions on your manifold M. So if you find theta such that its pullback satisfies this equation, so first you pull back your function to the product and then act by a vector field, or first act by a vector field and then pull back. And if those two things are equal, then this is precisely this, and this is precisely this. So this kind of looks nice because whole graded geometry and the graded smooth maps between graded manifolds, they are always defined in terms of pullbacks of functions, because graded manifolds are defined just in terms of functions, not in terms of points and spaces. Okay, and this finishes the part about ordinary flows. So this is just a kind of quick formulation of what you know from the favorite textbook. And then you can talk about, and then we'll divide actually the discussion into two parts. And one will discuss the flows of degree 0 vector fields, and one will discuss the discussion for non-zero degree vector fields because they are vastly different to each other. So let me discuss the degree zero flows.
I'm just trying to understand the notation. So one tensor dt is supposed to be something which takes a function and returns a function, right?
Yeah.
So don't you need to accompany by multiplication and variables?
You mean in this formula?
Well,
What I mean is
in the definition, you're writing down one tensor dt.
It's just a notation, so don't worry too much about this. This is just a notation because kind of naively you can imagine the functions of the Cartesian product as a tensor product of two algebras of function.
Yes.
And so this is really kind of tensor product of identity acting on functions on n, and this thing as an operator acting on functions on R. But this is not really true. The Cartesian product, functions on Cartesian product are not tensor product of two algebras of functions.
Yes, you somehow need to go back to functions on cross R.
Yeah, but this is just a notation. Just in local coordinates, just imagine this is just a vector field which calculates the partial differentiation with respect to this parameter t as a coordinate on R, and that's it. There's nothing more into this.
Just partial derivative.
Partial derivative. But you can do this always. So you can lift not just this vector field, but you can lift any vector field from R in this very same way. So it's just a convenient notation. Really don't worry too much about this tensor product. It's not tensor product of anything. It's just a notation. Okay, so now.
Sorry, may I comment?
Yes.
Yeah, I mean, maybe it will be. Maybe you can make like like instead of 1 times partial, you can also write it. This is like 0 tensor 1 tensor partial. That will be more in line with the.
You can write it probably in many different ways, but it's very. I don't want to
No, I was just trying to clarify like that's the connection with like infinitesimal whatever derivations. Like you can imagine that there is like a first term which is like 0 tensor 1 plus this one.
Yes, you're right.
Okay. Yeah.
Don't try to overthink this. It's
Right. Yeah.
It's just the vector field which differentiates with respect to this parameter t, because all your functions depend on points on n t. So now curly n might be a graded manifold. So I don't want to spend too much time on explaining what is a graded manifold. So the important thing is that each graded manifold is some sheaf of graded commutative associative unit out, means that they have a unit into algebras on some topological space M, which is second countable house of topological space. Which means, what does this mean? That for every open subset U, so every open subset of this topological space, you have an algebra. You have a graded commutative associative algebra with the unit. And these elements of this algebra are simply called functions. On this curly n, probably over some. If you want to specify that they are just local functions, that you say they are over U, and because it's a sheaf, you can restrict from bigger open subset to smaller open subset, and because it's a sheaf, you can do functions which agree on the overlaps global limits, you can compare things locally, etc. So this is what it is. Each function, because it's graded commutative, and by graded I always mean z-graded. So every function has associated degree, which is an integer, the degree of that. In our formulation of graded manifolds, we in fact do not have inhomogeneous elements. So for us, every function has a degree, and that's just technical detail. And also every function has something which is called the body of the function. So every function has a body, which is an ordinary function on U. So in particular, it turns out this kind of consequence that M is actually manifold, smooth manifold. So you can talk about smooth functions on your underlying topological space. To each function you can assign body, which is an ordinary function downstairs. And note that, just note that the body of the function is 0 whenever the degree of the function is non-zero. So only degree 0 function has some possibility to have a non-trivial body. All functions of degree different from 0 have automatically trivial body. Okay, so this is the notion, just a notion of a graded manifold in a really quick nutshell, so I don't want to spend too much time. And then we talk about functions between, or maps between graded manifolds. So what is a map between graded manifolds? So if you have, we write it suggestively as one would expect. So what is a graded smooth map? Is a pair. So it's always a pair. And there is some phi underline and phi star. And where phi underline is a map of the underlying manifolds, which is smooth. And this phi star is in fact not a single map, but it's a collection. I'm intentionally vague here. So it's a collection which goes over all open subsets of this manifold here, and where phi star V always goes from algebra of functions over V to the algebra of functions on curly N over phi underline inverse of V. And this collection has to be natural in V. And they have to be algebra morphisms, graded algebra morphisms. Right? And there are some technical assumptions again. So all those things are graded local ring spaces, and these maps have to be, they have to induce morphisms of graded local ring spaces, blah, blah, blah. But basically, this is just a collection of algebra morphisms between the algebras, which are natural with respect to restrictions in some sense. And how do and there is another thing which I have to tell you, that graded manifolds, of course, have to locally look like something. So this is kind of a global picture, but you want them to locally look like something. And I will tell you what the something is. Okay, so there is always some sequence of non-negative integers labeled by integers. So some sequence, and it's finite sequence. By finite, I mean only finitely many of those is actually a non-zero set of non-negative integers, non-negative integers. And this sequence is called Grady dimension. Or is curly n. And basically what it says is a collection of non-negative integers where nj is number of degree j coordinates or local coordinates on curly n, whatever that means. Okay, so this basically tells you how many of which degree coordinates you have on your manifolds, and in particular n0 is just dimension of, it turns out that n0 is dimension of the underlying manifold, because this is exactly the number of degree 0 coordinates, and only degree 0 coordinates I have are those on the base manifold. And locally, and I will again be very vague, so locally we have two kinds of coordinates. We have x coordinates, and which are labeled from 1 to n0, because we have precisely n0 degree 0 coordinates. And there is some number of non-zero degree coordinates, where this number is precisely the sum of all the other expected for 0, 1. So this is just sum over non-zero j's of nj's. And the rule is that xi commute with everything, and those xi's, they commute with respect to each other using the rule depending on their degree. So I kind of impose this. So I assume that I have some coordinates which do not always commute, but those xi's, they either commute or anti-commute depending on their degree. And locally, each function on n can be expressed as form of our series in the following form. So it's a sum over sum, and I won't go into too much details what this sum actually is. So the point is that coefficients of my formal power series are ordinary functions of these ordinary coordinates, and they are formal power series in those other coordinates. And what's the notation? So this double P is just an n star index. So it's an n star index. And this psi to this n star index is just you take psi1 to the power p1, psi n star to the power p n star. And this strangely denoted set here is just a set of all n star indices such that these guys are actually, first of all, non-zero, and second of all, if you kind of look at their degree, pretending that degree of a product of two variables is some degrees, then this kind of monon here has to have precisely the degree same as the function. So this is how locally your functions look like, and I won't tell you explicitly what it means locally look like. It means that there is some sheaf isomorphism of restriction of your sheaf to sheaf of those formal Pauli series defined on some open subset of R and 0, blah blah blah. But it's not really important. Just imagine the functions that they are globally defined, but locally you can work with them like they are formal Pauli series. The product of the function is just the product of formal Pauli series, except you have to rearrange size afterwards, and you cannot do that like for free, but you have to pay some signs based on this rule. So this is just vaguely what it is.
Yeah, sorry. So Kotov and Sarnikov have this Z manifolds.
Sorry?
Kotov and Sarnikov have this
Z
manifolds. I don't remember what the local model for that.
They have something. It's very similar. They are actually now planning to. Their approach is slightly different from the one I did in my paper on Z-graded manifolds. But we are not kind of planning to coordinate a paper where we will explain how they are related precisely. So this is basically what they have, and we believe it's the same thing they have.
I can imagine that it all boils down to choosing a specific recipe for multiplying formal power series. Or maybe they should have different convention concerning what degrees are allowed.
Yeah, it was actually not easy to invent this, because you always have to work with multi-indices of things, because you have some kind of formal Pauli series in some coordinates, and that you have finite number of coordinates. So you basically always sum it over some set of multi-indices, and you have to choose how precisely you parameterize this. So this was my kind of approach to it, because it's actually quite easy to work with.
Maybe you can classify all possible schemes like this. Put the associativity constraint, you want the multiplication to be associative, commutative.
Yeah, probably.
Maybe the different solutions give different models, like yours.
I don't think so. I think it has to lead to the same thing eventually. But I'm not claiming that. I'm just believing that. But I think they have the same structure. Because for polynomials, of course, it's clear how it has to work, right? For polynomials, you formally multiply the polynomials in those variables, and then you rearrange them in a way where you use this rule. And there is no freedom in basically how you can do that. And for formal Pauli series, maybe there is some freedom, but maybe if you already specified it for polynomials, then there is probably no. You probably have no options to extend it in different ways to formal Pauli series. But I'm not claiming that, and I believe that which in mathematics are two different concepts. Okay, so skipping this vague, my poor vague attempt to describe what Z-graded manifolds are, we can now forget most stable local coordinates and look on the vector fields, because that's actually quite easy to define. So vector fields on this calorie M are derivations or graded derivations of algebras of functions. So what it means to have some degree. So we say that this is a vector field of degree, some degree x. So always denotes degree on this curl M over some open subset U. Means that x is linear, R linear, degree X map of C infinity mu. So it's just a linear map on your graded algebra to itself, which raises the degree of all functions by x, such that it's a graded derivation. So this means that if you plug in a product of the functions, they hold this value through the degree of vector field appears here in this sign. Okay, and one can show that's a kind of straightforward that vector fields actually form a module, graded module over functions. Then they also form a sheaf, so you can take a small open subset and restrict your vector field. You have to use partitions of unity on graded manifolds to do that, so this takes some time, but everything is working as it should. They also form a graded Lie algebra, so you can take graded commutator of two vector fields and obtain a vector field of the respective degree. But this is clear. The graded algebra is the graded derivations form a graded Lie algebra. It's a well-known thing. Okay, but now it's quite easy because I have already erased everything. But it's now easy to formulate what is a flow because we've already prepared our field. So for definition, so X, but I will be strictly talking here about degree 0 case. So X is a vector field on my graded manifold of 0 degrees, so it has degree 0. And then a maximal flow, theta, is the graded smooth map from M cross R to cross M. So I have just replaced ordinary M with curly M. And then keep R as it is, because every ordinary manifold is also a graded manifold. It's kind of trivial inclusion of ordinary manifolds in the graded manifold. So maximal flow is a map from n times R to M. Having the properties on the erased board. Okay. Is on the erased board. Blackboard. With M replaced by curly M everywhere. So seems stupid, but we have reformulated things so everything makes sense. So those commutative diagrams of graded smooth maps, they can still be formulated. And they make sense. And also this, because I formulated this part that X has to be infinitesimal generator of 1 tensor delta t. This still makes sense because 1 tensor delta t can still be defined as a graded degree 0 vector field here. Therefore, you can impose this condition for kind of intertwining theta with the action of two vector fields, and everything works. I have some problems with adding s's to my words, so everything works as expected.
So the parameter t is always of degree 0, right?
Parameter t here is always of degree 0, and I will explain you why.
So it doesn't generalize in super case.
It doesn't generalize super case. That's good remark, which will come to question also later.
Mm-hmm.
So first notion is that this vector field has degree 0, right? And this is why we have to consider only vector fields of degree 0 here, because this condition this condition that x is theta related, or no, the other way around, so 1 over tensor delta t is theta related to x. This only makes sense if this vector field has the same degree as this one, because this intertwining with respect to theta star is a morphism of gradient algebras, therefore it always preserves the degree. So x raises the degree by some amount, then theta star preserves it, and it has to be the same as action of 1 delta t. So the degrees don't add up if x is not on degree 0. Or you can think it's the other way around, so if x is on degree 0, then this manifold here has to be n times r in what I want to do. And this is big difference to your question with supermanifolds. Because for supermanifolds, they choose space, this space here.
Choose any such supermanifold of this guy.
Sure, yeah. But the thing is that kind of this contains both one even parameter and one odd parameter, and you can even combine them together. So in fact, to integrate all the vector fields, you have to combine non-trivially these two coordinate vector fields here. But the problem is that you cannot somehow canonically produce any R containing all the parameters of all possible variables, because it will be infinite dimensional space. So this isn't really working. This is the problem for gradient setting. And this will also be the bigger problem later. So up to now, this is not a problem. So up to now, this has made sense. This is what I'm talking about. Okay, sorry, my English is very broken. And the second notion is that every degree 0 vector field has an underlying ordinary vector field. So there is a unique vector field x0, which is ordinary vector field on M, such that it's actually defined by this equation. So x0 acting on the body of some function is the same thing as acting by x on f, and they taking the body of the. There is a unique such a vector field. Always for degree 0x. For non-zero degree, you can also define it to be 0 by design. Okay. And one can always show that the underlying smooth map, because this is a map of gradient manifolds. So map of gradient manifolds is a pair. One is a pullback of functions, and one is a underlying smooth map. And this underlying smooth map has to be flow of this x0. The maximum flow of x0. So kind of necessarily. So in fact, if you prove the theorem which I will tell you next, that there always exists a maximal flow, then you can start with this observation. So first you construct x0, construct its maximal flow, which I denote as theta 0 in the following proof. Okay. So just to give you an example, how the flow looks like. So there is kind of nice canonical vector field of degree 0 on every gradient manifold, and it's easy to find its flow explicitly. Okay, so some nice example. There is always a canonical vector field, which is denoted as E, and it's called polar vector field. And it's a vector field which takes function and multiplies it by its degree. So this is a vector field on gradient manifold of degree 0. Preserve the degrees, it just multiplies function by some number, and it's almost trivially a vector field. And this is called Euler vector field. And its underlying vector field, so E0, 0. You can check that if f is of degree 0, then it does nothing. So in particle, this equation is So E0 is 0. Therefore, its flow, the flow of the underlying vector field from n times r to n is just projection. So flow of 0 vector field is just a projection. So theta 0 mt is just n for all mt's. And how does this theta star look like explicitly? So you take function on n, and you produce some function on n times r, and basically you can first pull back function from f to the product by simply pulling it back by projection. There is always from Cartesian product we have because it's in fact it's a product in the category where it's manifolds with projections, which are things universal, etc. So you can pull it back from the base to the product, and this is a function, and you will multiply this function by a number, and this number is e times, and this is where the parameter t appears in this exponential. So if f is degree 0, then it's just pull back, and this corresponds to the fact that underlying vector field is just a projection, and if it's not 0 degree, there is something that will happen. And that's it. That's how it looks like explicitly. So at least for a vector field, the flow exists. And but there is theorem, which says that the theta exists. I don't have too much time, so I will skip technical detail. The maximal flow exists for every degree 0 vector field. This also works for non-compact manifolds, so everything works, including the flow domains of things. So and the proof is surprisingly difficult. Like no, not difficult, but it takes some time, and it contains some non-trivial observations. So just a big quick sketch. So of course the first step is find theta 0, like the flow of the underlying vector field, which you can always do. So you have it for free. Not for free. Our ancestors paid, hard work and grant money, probably. Not, I don't know. Their own money, maybe, to find this. And then just to be completely simple, you have to, like in ordinary case, you have to first work things out locally. Like if you construct flows in ordinary geometry, you kind of make it into a system of ODEs and use existence and theorem for ODEs to find your flow, and then you kind of extend it by some maximality to maximal integral curves, and then you prove it's your maximal flow. So let's assume now that our gradient manifold is just, and this is precisely the sheet of those formal power series I told you before. So for simplicity, assume this, and just then it takes some more work, but to see the idea. So it can be proved, like it's statement that every morphism of this so-called gradient domains is uniquely determined by looking at the pullbacks of coordinate functions. So you only have to know the pullbacks of coordinate functions, and you can work out the formula for the arbitrary formal power series, how it works. So basically what you have to know, you have to know pullbacks of disk size and pullbacks of axis, right? And the pullbacks, this is some formal power series on n times r, but since you edit no, so there's this subset, I will just write here P. And because you didn't add any new graded variable. These are still just formal power series in size, right? Except that the functions underlying here depend both on base manifold and both on your new variable t. So, and you also get another, and I denote this simply by different symbol, like it's just a symbol. And these are the functions you look for. Like these are you want to find those functions to determine theta star. And if you find those, you are happy, right? And you immediately see that there is one quite a big problem, that these sums are infinite sums, right? So you're like looking for equation for infinitely many variables. So it was not clear at all from the beginning whether it's even solvable, right? It will lead. It will of course lead to some systems of ODs, but who knows whether the system is not too complicated to deal with. So I was scared of this, and I kept this line for like 3 years. I know at this moment that I won't finish in time. Are you ready to be here another 20 minutes?
We can continue next time with your talk.
But I don't think I have the full talk for next time. Like it's so like half
talk and somebody for another half talk.
Just let me finish this proof,
okay.
And then we can decide. Okay, so and how do the equations look like? So this is kind of your parametrization of what you are looking for. So this is setting the problem, and now that's kind of writing down the problem. So what are the equations? So in fact, equations are very easy. So for every not very easy. The left-hand side equations are very easy. So left-hand side, it's always just derivation with respect to t of this function. So maybe I should write partial derivative here, but I want to look this OD-ish. And on the right-hand side, there is always pullback of x acting on psi mu. So this is some graded function on manifold M, and you pull it back. And in fact, this thing here is a pullback of infinite formal power series using another infinite power series. So this is kind of not a product, but it's you can compose. You can plug another formal power series to formal power series to getting another formal power series. It will be fine, but it's ugly, right? So this is formal power series, which is quite ugly, and contains all the possible components of theta and all the possible components of psi, x, because x of psi mu is again formal power series defined by the vector field x, and there's another second part of the system, which is of course system for all these other ones. So. And this is infinite system of autonomous ODEs for infinitely many variables. So okay, so one can be scared at first, but luckily, one can solve this system inductively, like iteratively. I don't know, inductively or iteratively. And what's the induction step? It's the weight of this multi-index. So you can define weight of this multi-indices, which is pi1 plus pi star. So this is some non-negative integer, right? And you can inductively solve it. So you first solve it for all multi-indices appearing here of weight 0, which means they are all zeros. And so let's call this W. So for W0, and this gives you not surprisingly, flow equation for θ0. So this is the flow equation for θ0. And now, induction stack is, so we assume that W is strictly greater than 0. And it turns out, what you get, you will get non-homogeneous homogeneous, some syllables here, for non-homogeneous linear system of OVs for your theta's and theta news of weight where the weight of is exactly W. So I should split this. So this linear part of the system, only contains theta, mu's, and p's, where these multi-indices have degree W. So it's a linear system in those of the highest weight. And this right-hand side, this non-homogeneous part, only depends on terms with where this weight is strictly less than W. So you really turn this, it turns out it takes some calculations, it's not difficult to realize this. So that's a good thing because you can solve this, right? Because every linear system of OVs can be solved with any, and everything is smooth, so all the parameters are smooth, so you get smooth functions out of it by solving those. And you can do this iteratively because you know already this non-homogeneous term, you know, by induction hypothesis, you know it explicitly as some function of x and t. You can plug it into equations and solve them. And
terminological note, you could say that you're solving the system hierarchically, where it has a
hierarchy.
Yeah, it's a hierarchy.
But I won't be able to pronounce the word probably. So I use the word iteratively. It's much easier. Hierarchically. Okay, and there is one crucial point here, which is very important, because this system is really a linear system of OVs. It can be solved for all R. That's very important. So it can be solved for every starting point, for every initial condition. It can be solved for arbitrary R. So your domain for a flow is not shrinking in each step, which is very important because otherwise it could, and this induction can go to infinity, right? It's not stopping. So if it would shrink, you can get to trouble. But fortunately, you are not getting into trouble because everything is working nicely. This is not restricting your flow domain, like anyhow. And it's still the same as, and the result is that the flow domain for ready flow is in fact the same as the flow domain for θ0. So the open set where everything works is the one you obtain from θ0. So only this x0 kind of directs the completeness of your vector fields. Okay, and so this is how you locally do it. So this is the most crucial thing. And then I will only finish by commenting. So you first observe this thing. I didn't tell you this one. Of course, there are initial conditions. I didn't tell you. There are some initial conditions to this OVs, of course, plus initial conditions, right? Otherwise, you would be. So you can solve it uniquely. There is no problem. And then you have to work globally. So if you want to work globally, you somehow have to use local coordinates on n to first produce a flow on some neighborhood of n times 0. And then you say, okay, so I will take union of all flow domains and extend them because it's a sheaf. So on intersections, they have to agree because they solve the same OVs, blah, blah, blah. So you have to work this out, really, to the extent of proving that it's really defined on this domain for theta 0 globally, and then after action, this still has to be proved, and it's not anyhow restricting your solutions. So you don't impose it anywhere, so you simply solve these equations, and then afterwards you prove that it automatically solves, satisfies these group-like equations. And the reason is, again, kind of uniqueness of the ODE solutions, as is in the standard case. You simply shift your parameter by a fixed number s, and then solve the equation in T and prove that it's the same thing as if you compose it. And this is what you have to use here also, some careful. It's not that easy, but it's doable. And this finishes the proof, this schedule. So this is how it's proved. And unfortunately, I don't have time for non-zero degree flows, which are much simpler. Like they are completely trivial compared to this. But I can start next week and in first 15 minutes tell you. I don't know how to do it. Or I can just tell you that it's working. But it's the most, on the other hand, it's the most interesting part, right? Yeah.
You can decide afterwards. So thank you very much.
Okay, thank you.
This is some space for your questions.
Sorry, if I'm mistaken, you said that there is no compactness assumption on n.
Oh, it is. Yeah, all the time.
Okay.
All the time. Otherwise, you have to discuss domains. Like, if n is not compact, then this theta 0 is not defined on the whole n times r, and also here then you have to restrict this graded manifold to some open subset. In fact, the same open subset as theta 0 is defined on. So yeah, it works for a non-compact case, but you have to be more careful with domains of your maps. That's the only message. Everything works, but you have to be a bit more careful. And I didn't want to spend time discussing this here. So I assume all the time, all my manifold and this non-curly and this underlying manifold is compact. Therefore, this x0 is complete and the flow is globally and everything is global. But it works for a non-compact case as expected. One just has to be more careful.
You can rewrite the entire definition with dual language of the by using what was on the rest level. I mean, you can restate everything in terms of coaction of algebra, such as this R, on your on the output of your created functions.
Yeah, probably yes, of course. But I didn't want to go into. I don't like this algebra too much because the product is not really a tensor product. You have to complete somehow with respect to something which I'm not still very sure how it works for gradient. It probably works also for gradient manifolds. Why not? But yes, I did want to skip this. So I wanted to be as with all my stuff about gradient manifolds, to do it in the way which will resemble the classical case as much as possible. So you don't have to use any knowledge of algebra necessarily to work things out. And everything then can be handled as is in the classical case. That's the main idea.
Any other question?
So this proof that you presented, this is, I guess you worked out the details for the Z-grade manifolds for your model. I presume that similar proofs were already given for n-graded.
For n-graded, it's actually much easier because if they engrade and however, there are problems. That's one thing actually that these flows of vector fields actually are the reason why you should not work only with n-graded manifolds. Because in n-grade, the problem is that vector field has the opposite degree to the coordinate. So if you have coordinate of some number, k, then d over d psi is of degree minus k. So you can have negative degree vector fields, but you can also have positive degree vector fields. You can have vector fields of both degrees. So your parameter, which I will introduce next time maybe. So if you work with vector fields of non-zero degree, then this parameter so the space here will have coordinates of the same degree as the vector field. So it has to be sometimes positive, sometimes negative. So it's really, you need essentially both notions. You can maybe work with non-negatively graded or non-positively graded, and everything will be just polynomials. It will be much easier. So for ungraded, it will definitely work to some extent.
But like, do you know that somebody worked this out, Ida, or people
No.
explaining that this is?
I don't think they actually. I think they never discussed flow on. They do it for supermanifolds.
Okay.
There's plenty of papers on flows on supermanifolds, and the story for odd vector fields is very complicated. Not very complicated. There are some problems. For example, you cannot. It will turn out next time that in my description, odd vector fields only have flows when they are homological, they square to zero. Otherwise, they don't have flows. Simply, they don't have flows. And the same thing happens in supermanifold if we want to take this parameter to be, this vector field to be only d psi, the single parameter. And the reason is simply that coordinate vector fields commute or anti-commute all the time, whereas a vector field doesn't have to anti-commute with itself. This is basically the reason why it doesn't work. So they mitigate it by considering, as I told you already here, instead of having just R with one odd variable or one even variable, they have both together. And they mix up some vector field on this one-dimensional supermanifold such that it works. But then, in fact, they prove that there is no super regroup action which actually makes it into action of the super regroup. So you can either solve one problem and don't have the second one. So it's still not working completely even for supermanifolds. There are some issues. It also depends what you want your folds for. So I want them for Frobenius. There you can work just with coordinate vector fields, which anti-commute with themselves. So I think this will be satisfactory for our purposes for proving Frobenius for graded manifolds in the future.
So just about the structure of this proof, which decomposes the flow into this infinite system, hierarchical system. I mean, that's quite an old idea. So at least in for supermanifolds, there's some old work by Choquet-Brouillard coming from relativity. This came up when supergravity. People wanted to understand what is a solution to a PDE where the unknowns are also.
Yeah, they of course have.
Yeah.
So these papers about flows, they also solve this kinds of equations.
So I mean that was already even more complicated. So there had some PDE system which also decomposed in this hierarchical way. So that was back in the 80s.
Yeah, I suppose.
And with maybe a very short question concerning your last comment. Did you mention by saying that you can glue these solutions, local solutions together, the fact that you can promote it to some sheaf morphism?
Yeah.
Okay, so this is, are you gonna to say something more next time, or?
I can maybe, but it's funny. You have to do it somewhat differently, because in classical case you simply prove that at every point you can construct integral curve on some open neighborhood of zero, and then you say, okay, so my maximal integral curve is that I kind of take all the integral curves I have and I take union of all the domains and then prove that all integral curves have to coincide on the intersection of their domains. This basically gives you that it defines the global maximal integral curve. You collect the maximal integral curve, and that's your flow. This is how you do it classically. Here, this is not really possible because you are not working with integral curves. You are doing the maps, like the whole maps from the Cartesian product somewhere.
Yes.
So you basically you have to again prove that if you have two flows defined on two flow domains such that their flow domains intersect, which they always do, that then on the intersection they have to coincide, and that's not that easy. Right? There are some. It's not complicated, but it takes some different approach from the classical case because you have to kind of glue together kind of all the squares going to the zero section. Okay. I don't want to go into details too much because it's just technical. You just have to carefully compare things locally and from it conclude that it's well defined.
Yeah, it's option for me. Okay.
Just one more. You said next time you cover the case of higher vector fields.
Vector fields are non-zero.
Yeah, you said that the homological ones are integrable. So if you consider the vector field associated with the algebra, so integrating this will give the action of like
R shifted by the degree. R is 1 or -1.
That helps you better describes various constructions like current algebra and the algebra zone in terms of action.
Yeah. But the point is the flow of odd vector field is in fact almost trivial thing. So I don't know whether you get something interesting out of it because it's very easy to do. It's basically for this non-zero degree case, you can think of flow as exponential. Really, then it really is exponential in some sense. And for odd vector field, there are only two terms in this exponential, so you get one f plus x f in one f, and that's your flow. Times this parametric size, so it's not that interesting, unfortunately. I will not tell you next time. I could have told now. Long questions, but thank you.
So, any other question? Not the case. Thank the speaker again. You may look forward for Jan's second part next time.